So let us now differentiate the function x squared from first principles. So we know x squared is a parabola. We know from the shape of a parabola that its gradient is always changing, and so the value of the gradient at any point is different to another. So what we'd like to do is come up with a function that can describe the gradient for us, that we can put in an x value and it'll give us a y value, which is going to tell us what the gradient is. So first principles, we need to remember what the first principles formula is. So from first principles, we know that the gradient function, which we call f of x, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So that's our change in y over change in x, and we set the distance between the 2 points as h. All right, so we've got our function here, f of x equal to x squared, and we're going to apply our formula for first principles to this function. So f of x, or f dash x, so the gradient function, is equal to the limit. Now we have to keep writing this, the limit as h approaches 0, until we actually evaluate the limit. And until we do that, if we don't write this limit at h approaches 0, then we're not looking for the gradient function. Then we are looking at two distinct points that are separated from each other, and that is not the gradient of a single point. And so we'll keep this limit as h approaches 0 until we are finally able to assess this limit. Now we can't put 0 into this equation at the moment, because if we do, we'll have 0 on the denominator and that would not be valid. Okay, so my function is x squared, and into my function x squared I want to put x plus h. And so what's going to happen is we're going to replace x with x plus h, and that's x plus h squared. And then we're going to take away f of x, and in our example, f of x just happens to be x squared. And now I'm going to divide through by h. Okay, we can do a simple binomial expansion. So here we have the limit as h approaches 0 of x squared plus 2xh plus h squared, and then we have that minus x squared all over h. Now we can already see the x squareds are going to cancel out nicely, and we have a common factor of h in the numerator, so we're going to factorize that out. So we're going to get the limit as h approaches 0 of h 2x plus h all over h. So now we're finally able to cancel these h's out, and that's good, because now I don't have h on the bottom. I can actually look at what happens as this thing approaches 0. So we still have the limit as h approaches 0 of 2x plus h. And we're now finally able to assess our limits. So what we do when we assess our limits is we look at each term individually and we go, right, as h approaches 0, what happens to 2x? And the answer is nothing, because there's nothing to do with h in 2x. And so as h approaches 0, 2x stays 2x. And then we look at h. As h approaches 0, what happens to h? Well, as h approaches 0, then h becomes 0. And so now we've assessed our limit, and we can stop writing this limit as h approaches 0. Okay? And we are finally left with our gradient function, which is f dash x is equal to 2x. And so that's how we differentiate x squared from first principles. We can continue this idea, and we can differentiate x cubed minus 4x from first principles. Right? It'll give us a better understanding of where the rules of differentiation come from by evaluating what this looks like. So again, we are differentiating from first principles. So we need to state what we're about to use. So first principle says f dash x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So that's my change in y over change in x. Change in y, change in x. And that's the definition of gradient. All right, so this is equal to the limit as h approaches 0. And now I need to plug x plus h into my function. My function is x cubed minus 4x. So I'm going to have x plus h all cubed minus 4 times x plus h. There's my x plus h into the function. And I'm going to subtract x cubed minus 4x. And it's important that we put that in brackets so we don't lose the track of the double negative there, all over h. And now we need to expand this out. Now, fortunately, we've already done binomial expansion, so this cube expansion should be pretty easy. So we're going to have x cubed plus 3x squared h plus 3x h squared plus h cubed. And expanding the other bracket, we get minus 4x minus 4h. That's my f of x plus h. And then we have this minus x cubed, and the double negative is going to become plus 4x. And this is all over h. So once again, we'll see that we can cancel out the x cubed terms. We can also cancel out these two 4x's. And in every one of these terms, I have at least one h, and so I'm going to factor it out in the next line. Right, now we still haven't assessed our limit, so we have the limit as h approaches 0, and we're going to pull an h out, and we're going to be left with 3x squared plus 3xh plus h squared minus 4 all over h. Okay, so we've pulled an h out of all of those terms. Now, like before, we can finally cancel out the h in the denominator, and that's good because now I can assess the limit as h approaches 0. Before I couldn't, because I can't assess the limit when I have 0 on the denominator. So this is equal to the limit, and we'll just tidy up so we can see what's going on. We have the limit as h approaches 0 of 3x squared plus 3xh plus h squared minus 4. And so now we're finally ready to assess our limit. So we're going to take each term one at a time, and we're going to assess what happens as h approaches 0. So in the first term we have 3x squared, and as h approaches 0, 3x squared doesn't care. It just keeps on being 3h squared. The next term we're going to look at is 3xh. As h approaches 0, right, h is getting closer and closer and closer to 0, that it gets to a point where h is so small and it's approaching 0, it becomes 0, and anything multiplied by 0 is 0. So as h approaches 0, 3x times h also becomes 0. And the same thing can be said for x squared. So as h approaches 0 and gets really, really small and close to 0, the values for h would approach 0. And you can test this out in your calculator if you want. Put in smaller and smaller and really small numbers for h, and you'll see it just gets smaller and smaller and closer to the value of 0. Right, and finally we have minus 4. Minus 4 doesn't care about h. There's no h's attached, and so it stays minus 4. And so we get our gradient function f dash x is equal to 3x squared minus 4. And I'm sure because you've learned the power rule at IGCSE, you will notice that it differentiated exactly the way you expected it to. However, now you have an idea of where the idea for the power rule came from. It comes from the fact that we noticed a pattern when we learned to differentiate functions from first principles. Okay? And now every time we look at a new type of function, right? So when we look at exponential functions, trigonometric functions, we're always going to look at how we differentiate them first from first principles before we're able to learn all the little tricks that we learn in order to differentiate things slightly faster. So obviously, differentiating from first principles is not something that you need to know how to do, right? You can see that it's quite long and cumbersome. Obviously, differentiating using the power rule and the other rules will be much more faster, but it's always good to understand the mathematics behind all of these rules.